Thank you so much for organizing this conference. This is the first after COVID real conference, hybrid conference that I'm attending as a speaker. And I feel excited like a small baby, you know, something new is happening. And I would like to thank the organizers because I know that it wasn't easy to organize it in these circumstances. I would also like to thank Thomas and Laura for inviting me to give a talk in this special session. Now, my talk is going to be, let us say, more utilitarian, or perhaps in the philosophy of mathematical practice, as they call it today, because I would like to discuss something that we don't normally discuss, soundness or truth. So here is the young Kurt Gödel at the time when he proved the theorem that we are celebrating in this conference, theorems that we are celebrating in this conference. And so he proved many things that were our guiding light in logic, have been our guiding light in logic ever since. So, of course, his completeness theorems, which was his thesis work in 1929, which states that every first-order sentence that is true in all interpretation of a first-order system is provable in that system. So, in other words, every tautology is a theorem. The soundness theorem says the opposite. Everything provable is a tautology. And then we have the incompleteness theorems that are the basis of this conference, the reason to meet for this in this conference. So if a consistent first-order theory sigma is effectively axiomatizable and proves a certain amount of piano arithmetics, then it's not complete with respect to the set of first-order sentences expressible in its language. And in particular, sigma cannot prove its consistency. Of course, these things are stated here just to remind us, or to remind perhaps those, if they are in the Zoom audience, those who are newer to the field, what these things are. And to really state all of this correctly, we need to discuss many things, such as the idea of interpretation and models, which came after Gödel by Tarski in 1936, and meta theories. So these theorems have been a source of interpretation ever since. Most people think that in mathematics we have understood them completely and that it only remains to philosophers to discuss them. But I think there is something to discuss in mathematics as well. And in fact, the one of those theorems that is least discussed is the soundness theorem. And I would like to discuss that concept a little bit because it's about verifying truth. So there are people who talk about the soundness theorem, even in the mathematics community. For example, Kay wrote this paper in 2014, in which he sort of claims that the soundness theorem is circular. Other people talk about the relation of the soundness theorem to the philosophical concept of logical consequence, which is not such an easy concept to define, and it is open to interpretation. So Dresden says that any position with respect to the later issue, the nature of logical consequence, will have implications to the former. And I think that in mathematics now, we should perhaps think of this question. And I will say why I think that. Most people think that this is, again, just a philosophical discussion. There is nothing to be said on the mathematical side, since the mathematical truth of these theorems is established. If you think of this just for 1 second, you will see that even in the mathematical community, we immediately have at least 2 different points of view, which of the direction of the equivalence between the provability and the truth is the one that we should kind of feel comfortable about. So the first point of view is the truth in capital letters is true in what is true in all models. So this semantic point of view which well, is very present in subjects such as set theory. And the second point of view is that truth is what can be verified. Well, of course, there are other positions, for example, that there is no truth with the capital letters, so the formalist position. But for the purpose of this talk, we'll only discuss 1 and 2. So according to which side you take, the soundness and completeness take different meanings to you philosophically. So in mathematical logic, this view 1 is mostly represented by set theory and model theory, which work in semantic way, although in model theory there are schools, there is a semantic school and syntactic school. And in 2 by the proofs theoretic community, which concentrates on proofs. Personally, I think it is, well, as you will see in this talk, I feel that the best knowledge that one can obtain is by looking at many different directions, not just in one. So in a sense, I think one should be looking at the intersection or the union of these two talks, of these two views. So there are many things to discuss here, but the one question that I would like to talk about today is how to really make sure that the proof is true or correct. And I claim that this question has changed its meaning from the time that Gödel and his contemporaries were discussing this. The proofs have changed. So let me say a few words on that. So what are verification processes that we have of proofs? Of course, a person writes a proof and verifies what he or she has written to the best of their ability, but this is not enough. We should get this verified otherwise. So classically, when I was a postdoc or wrote my first papers, what we would do is to first, of course, have the proof read by a colleague, then send it to various people, wait for a few months to see if there is some objection or comment or so. If not, then we would send this to a journal. Then this would wait for the referee report, sometimes 2 referee reports, then we would react. Well, this was a very nice process that took about 2 years at least from finishing the presentable version to publishing. And the way that we hire new people today does not allow for this type of verification process, because we ask our new PhDs, that even when they come for a postdoc, to have already produced something. So this way of verifying, unfortunately, is now no longer practical for our more junior colleagues. Luckily, we have the archive, so we deal with this question by publishing first on the archive, which is a fantastic thing to have. Then we deal with objections for a while, send to a journal, and do as above. Again, this is a process that, because of the social pressure, has been shortened by necessity. People publishing in journals that do not take enough time to referee, referees that do not have enough time to read, etc. So this is not a very perfect process. How about the ideal? I started my life as a Platonist, and even though I'm a pluralist, still somewhere I believe in some ideals. And the ideal would be that we have our proofs verified independently. So since the humans don't have the time and the resources, maybe by a proof assistant. That would be very nice. Of course, I'm not the same one the only one that thought of this. So let me say why something about this third way. So we start from the assumption that the first 2 verification systems are not ideal, since the lengths of proofs and the number of papers have become of exponential complexity compared to the number of referees and the time available. And not the only, but probably the most known and the most courageous person to have stated this very openly was Vladimir Weizsäcker. Vladimir Weizsäcker was a winner of the field medal, somebody who worked in a very complex part of mathematics, who, before winning a field medal, produced a very complex argument, which was found to be wrong. But he did get the field medal for something else. His proofs were incredibly lengthy, difficult, and he realized that, in fact, people were not reading his proofs. That's what he said in an invited lecture at the ASL meeting in 2013, where I was present. And he described that this changed his opinion of the mathematical community, and he felt that he would like to have some way of formally verifying his own proofs and other proofs. And he was, well, of course, you probably know the story of Weizsäcker. He was obviously, I knew him very little personally, but he obviously was a very intense person. So when he wanted to do something, he did it well. So he got involved with the Koch community, went to work on proof verification, developed homotopy type theory, and univalent foundations. And these foundations communicate really well with proof verification, for example, in Koch. So for a while, it looked really like a magic solution to our problems. And there were all these conferences organized in which people would come with computers, writing libraries, claiming that all proofs will be in computer libraries, that mathematics is coming to this new era in which we are going to have something like a Wikipedia mathematics in which everybody will communicate their libraries of proofs and so on. And it looked great. Well, I must say that it didn't really look so great for set theory, because unfortunately this type of foundations or homotopy type theory is not everything for everybody. And there are some things that it does not found. They are unfounded in these subjects. So simply some parts of mathematics are well expressed in these foundations and some are not, exactly like in set theory. And it happens to be the case that set theory is not well presented by these foundations. That is, some of the most interesting questions in set theory do not even come into this framework. In particular, the consistency strength of a model of univalent foundations is at most that of ZFC. So Weizsäcker produced a model which used two inaccessible cardinals, but this was then reduced to ZFC. So obviously such a foundation cannot answer any questions that involve large cardinals. Well, you may say, who cares about large cardinals? We don't need them anyway. I do not think so. Well, perhaps I'm biased. We just seen Harvey Friedman in the audience. I think he has spent a lot of effort showing that some very natural questions actually in mathematics require large cardinals. But even if we forget about large cardinals, just some simple questions like the continuum hypothesis do not really have a meaning in this type of foundation. So an escapist answer is that we do not need set theory at all. Let's just forget about all that and do some other foundation. But this is an escapist answer because it cannot be taken seriously, because model theory is based on set theory, finite model theory is based on model theory, algorithmics is based on finite model theory. So we can enter here into some quite utilitarian, useful mathematics, because algorithmics is very useful, but even more so, we can go into one more step and find works of people who study complex networks, such as, I don't know, Facebook graph, and apply into it knowledge that comes directly from classification theory of Sahron Shelah, who is probably one of the most abstract mathematicians that we have, completely based on set theory. So we cannot just reject this part of mathematics. And I'm very pleased to be now working with Sylvain Schmitz at ERC in Paris, where I was able to learn some very concrete applications of this kind of mathematics in algorithmics. So, okay, we haven't solved the problem. The univalent foundations have not solved the problem of verifying mathematics. I happen to have a purely pluralist view of foundations, but this talk is not about that, or at least not completely. So let's try to see if we can do something for that part of mathematics that I happen to be practicing. So I think there is some uncertainty about as to when do we believe our own proofs. So like Voevodsky, I have dreamt to be able to certify proofs. Mine as well, but even more so those of great mathematicians who produce enormously long proofs. And I know it with concrete examples that often these proofs are not understood or verified even many years after they have been found. I know of a concrete proof that I would really like to understand. It is now 45 years old and nobody understands it. And I think the author has forgotten about this proof. So there are proofs that, and this is not something that we do not use to build other theories on top of this proof. So there are proofs in present day mathematics that need to be verified. Sometimes the author will miss something on page 125 of his long proof, and it will mean nothing to this particular author because he might have a vision, but others might not see that vision from the writing. So this is very difficult, and it is topical because things are getting more and more complicated. I have also noticed that certain parts of mathematics where I work, so combinatorial infinity, let us say, I have noticed that certain parts of mathematics haven't been able to move at all for many years, since nobody was able to read the proofs that are known. Papers have been left unpublished for more than 10 years. Actually, I found some that were unpublished for 20 years because nobody could read the proofs. New results were not obtained. And so I said, well, let me try to understand this verification business and try to move on some of these fields. So let me give you a case study of my own experience with computer verification. So I have hoped to use the verification and counterexample making tools of computer formalization to move on. So this is a case study. These are my two distinguished co-workers, Laurie Paulson, FRS from Cambridge, and Angeliki Kutsuku-Argiraki, working with Laurie. We worked on ordinal partition relations. So let me tell you what these relations are. Perhaps you know what cardinal partition relations are. The most basic one is the Ramsey theorem, which is present everywhere. It says if you have an infinite set, you color the pairs of this infinite set in two colors. There will be an infinite subset which has all the pairs colored in one color. There are versions of this, but this is the most basic one. Now imagine that you want to do the same with an ordinal. So you have an ordinal, you color its pairs into two colors, and you are looking for a subset which has the same order type as that ordinal, which is colored in only one color. And even weaker than that, you say, I'm happy to either have such a subset, or I have a counterexample in the other color of size 3. So that is what this notation alpha arrows alpha 3 means. So you are looking to characterize countable ordinals alpha such that when you color the pairs of alpha into two colors, either you find a subset of order type alpha whose pairs are colored in one color, first color, or you find a subset of size 3 whose pairs are colored in the second color. This question is still open since 1956. Erdős and Rado asked this question in 1956, and some results are known. And what we have done is to try to verify some of the available material in this subject, with the idea that perhaps eventually we could build some computer formalizing tools, such as counterexample checking, that would let the field move on, because it is exactly in this field that I know of 2 papers that have not been published since 20 years ago, probably because there is no referee for them. It's very complicated, things are very combinatorial. So we have this paper with Lori and Angeliki that's going to appear in Experimental Mathematics. And let me say then why we chose to work on these particular problems. Well, I think you will agree that countable ordinals are important, not only in set theory, but they appear everywhere in verification, in proof theory. But amazingly enough, modern set theory has very few tools to deal with countable ordinals, or ordinals in general. Most of these tools go back to Cantor's normal form. We have an enormous amount of knowledge about cardinals, but almost no knowledge about ordinals. We use countable objects, such as countable elementary submodels, but just as tools. So the only known results in this subject are due to brilliant but isolated individuals, and sometimes these results are impenetrable to others. And also, I think that partition relations are very important. Probably most of you know the fantastic book that Aki wrote on high infinity, in which you will find a chapter on partition relations, in which he explains how the partition relations have entered and motivated much of the theory of the large cardinals. So partition relations are very important for set theory, and I think that you can see it as once we knew partition relations, we could do other things in mathematics. Work of Stevo Todorcevic also speaks to this. So it is possible that once we understand partition relations of ordinals, we can understand more about ordinal combinatorics. So all of this is very important work. And so what have we done? So those of you who know something about proof assistants will know that Lori is the person who invented Isabelle. There are many proof assistants available. Here is the beginning of the Wikipedia page about proof assistants. So it only goes to the letter C on my slide. So there are many proof assistants, and some are better than others for various purposes, etc. I was impressed by Larry's work, which the first thing that I've seen is that he formalized the proof that from the consistency of ZF, you can get the consistency of ZFC. And I was really amazed that one can formalize such a proof in a proof assistant. So, well, some of you will perhaps know the work of Peter Kopke, who does Naproche, which is now, which communicates with Isabelle. Other people will know, of course, Koch, we already mentioned. Lean is a product that now has been taken by Microsoft. It is becoming a very, tries to be a very kind of community-based thing that people teach to undergraduates at the Imperial College in London. The undergraduates learn analysis in the class of Kevin Buzzard by learning Lean. So many people are very enthusiastic about this. People have formalized things in Lean, like Jeremy Avigad and his colleagues have formalized some serious set theory in it. So, well, let me not go into the discussion of which assistant to use. Like in foundations of mathematics, there is no uniqueness in this. And choices have to be made, but I think that whatever I have to say is independent of what we used. So let me tell you the conclusions. What did we formalize and how did it go? So we formalized a first paper from Jean Larson from 1975, so a long time ago. A beautiful paper in which she gives a shorter proof of an unpublished theorem of Milner, which says that for any natural number m, the ordinal omega power omega arrows omega to the omega m. This was several months of formalization work, mostly done by Laurie, who speaks Isabel as well as he speaks English. He invented Isabel. It took several months. A rough measure of the complexity of this formalization can be obtained by what people in this subject call the Bruin factor. It compares the number of lines of the formalization with the number of lines in the original. In this work, this factor was more than 20. Number 6 is considered high. So what do I conclude from this? For me personally, I'm not going to be able to formalize the proofs that I want to formalize. Because formalizing mathematics in order to verify proofs requires as much effort, if not more, as reading it classically. And I am more versed in reading proofs than in verifying them mechanically. Things do become easier when libraries of verified pieces are built, such as people have been doing in the HOT community, Lynn, Isabel, and other communities. But it is a laborious process which is not likely to catch up the totality of mathematics in real time. Although it may have some really strong and useful local results. But this is not going to solve our problem, in my opinion. It's going to help us solve our problem, but it's not going to solve our problem of verification. In fact, we have some incompleteness, an incompleteness which has sneaked out from a different direction than the formal direction that Gödel and his contemporaries have studied. It's an uncertainty that comes from the human side of mathematics, not from the formal side of mathematics. And this is an uncertainty that, well, we have to say that we are probably the last Mohicans in the sciences, that's in mathematics, I mean, that somehow refuse to deal with uncertainty. All other scientists, like physics, have dealt with uncertainties and have advanced. Computer sciences, for example, I have followed this very interesting, I have partially followed a very interesting course in the Collège de France by Frédéric Magnès, the director of IRIF, who spoke about quantum computing. So quantum computing is based on uncertainty. It's based on the uncertainty of quantums. And these people have studied so much the possibilities that this gives, that now when the first quantum computing chips are actually finally being made, these people are ready with the 30 years of study of quantum algorithms. They're ready for big things. One of them is breaking cryptography that we used for security, for example, in credit cards, this RSI algorithm. So all of that comes from being able to use uncertainty. So we should not be afraid of uncertainty. We have to deal with it. I don't know how, but I think we have to deal with the localized information, heuristic confirmations, pluralism in foundations. These things are somehow there. We have to deal with them somehow. I don't have the answers. We even have to deal with the social and community aspects. I found this very nice work by a philosopher called Bart van Kerkhoff from Brussels, who deals with that. He deals in philosophy of mathematics with the idea that there is a social aspect in accepting a proof. So all of these things, for me, are like the elephant that's in the room, and we don't want to speak about it. I think we need to speak about it. There is a problem. I don't have a solution. I wish to open this discussion with the logicians because I think it's the logic community that needs to lead this discussion. And searching for one perfect logic that will help us is not realistic. It's like searching for one single foundation of mathematics. It just doesn't work. There isn't such a holy grail. So just like in the incompleteness theorems, we have to somehow understand how to move in this uncertainty. And there are works in uncertainty logic. I'm not very familiar with that. I know a little bit. Perhaps some of that can be used to formalize the situation in which we find ourselves. Thank you.